groups together and then pick one of those days, 23rd, 30th, 6th, or 13th of November, I think, are the dates, but I might be wrong about the calendar. So let's start today's discussion with a look at the satellite movie over the continental U.S., and I chose to use the infrared because I had too many hours of darkness on the one that I could access. And there's a lot to look at. So you can see that beautiful cyclone that's roaring itself deep into the central part of the Labrador Sea. We'll say something more about that one in a few minutes. But it has an enormous scale. It has frontal clouds that go all the way down to the southeast of Bermuda, which is right there. So this is really quite an impressive extratropical storm. But there, as Morgan would say, he actually uses this foolishly as an argument against their awesomeness. They're a dime a dozen. That's right, they are a dime a dozen. I don't have to wait around for 15 weeks to get a storm, and yet they're beautiful every time. Here's Delta, though, to get really serious. This is a major hurricane. It's still a Category 3 hurricane. I think it has sustained winds of 115, which barely puts it over that threshold for Category 3, which is the first of the categories for a major hurricane. And it's now poised to make landfall, almost a direct hit, just like Laura, to the Lake Charles, southwestern Louisiana portion of the state. So the whole coast of Louisiana, from about this location here, which is almost directly south of New Orleans, all the way to barely across the border into Texas, is under hurricane watch right now. Tropical storm watches flank it on both sides, and it's already precipitating down over the southwest bayou and parts of Texas. So yet another major disaster for parts of southwest Louisiana, and the state itself has absorbed 6 of these things this year. So it's been a really bad year for tropical storms in Louisiana. So hoping that people who've already had their homes destroyed have some way to get out of the way of this next one. But it's a major event, and it looks like it'll make landfall. We'll say a little more about this. I guess I'll postpone that discussion when we get to the Hurricane Center map. This storm here will be the object of a considerable part of the current weather and past weather diagnosis. I want to show you some BIS 5D of aspects of this development over a period of time. I'll highlight those features of the development by looking at some upper level charts and movies of them leading up to this day today. And then we'll go off to the west coast. I'll show you some observations first of the current state, but you'll see that the next really big forecast event that will really dominate the weather over North America for the next 7 to 10 days at least, I'd say 5 to 10 days, is going to be the incredible polar subtropical jet combination that's coming in off the west coast. And we'll see that in the observations and then in a series of forecast panels. So that'll be my forecast focus for today, is what will happen in central North America. And I do mean central North America. It'll actually be central Canada, just north of our border. That will be a major development there that will dictate a lot of the terms meteorologically for us over the next week or so. So that's going to be fun to look at that. So let's go from this satellite movie to a depiction of the radar across the continental 48. So there is Delta, and you can see it even almost 150 nautical miles off the coast. You can see the center of Delta. It's never really demonstrated a picturesque eye at any point in its evolution and its track across the western Gulf of Mexico, and that's the case still today. But it's clearly got an eye wall convective maxima, even as it's beginning just to show up. We might see that better later in the day. It's got a northward movement of about 10 or 11 miles per hour, so it's headed straight for the southwest corner of the state, right near Lake Charles. And then out ahead of it, as is quite commonly the case, there's a rain band that stretches all the way into Tennessee and the border of the Carolinas. So that's probably moderate rain in many of those locations, but there stands to be 10 to 15, sometimes some places 15 to 20 inches of rain across the central part of the state of Louisiana. And then maybe as many as 5 inches in some other locations along the projected path of the, by tomorrow morning, tropical storm Delta. But overnight, and as it makes landfall tonight, it will be a hurricane. It's Category 3 now, as I said. There's a chance that it'll be weaker when it makes landfall, but it's still going to be a major event. But that is about the only precipitating feature across the continental 48. A little bit of light precipitation going across the Olympic Peninsula in Washington State, and then some lake effect precipitation coming off Lake Superior, but quickly disappearing into the radarless hinterland of Canada. They just don't have enough people living anywhere more than 50 miles north of the border, so the country is not instrumented and you lose some of the depiction of the radar summary as you go into Canada. So it's likely maintaining itself into Ontario, but just don't see it. Okay, let's go next to the West Coast satellite image, and this is a preview of what we'll talk about as the main portion of the forecast. You can see a clear cyclonic disturbance crashing onto the British Columbia coast. Some of the really interesting features of this map, to my eye, are despite, in spite of not saying much about these various little cyclonic disturbances, is the obvious difference in air mass between the northern side and the southern side of this cloud street, which is being carried along by, as you'll see in a minute, a pretty extraordinary jet. And so on the poleward side of it, the air is much colder. We'll see at 500 millibars, it's about minus 25 or colder. And so over an ocean surface that's about 10 C, 35 degrees over 5.5 kilometers gives you a moist, unstable lapse rate. And if you get a few convective plumes blowing up, well, they take off upward for free, and then the subsidence, at least while it's saturated, comes down for free, but then when it dries out, it's suppressed, and you can see, or it's forced. And you can see the spacing between the cells tells you something about the degree of the instability that you have in the updraft cores. And they're fairly widely spaced, so that's a fairly unstable, broadly unstable region of stratification over the North Pacific Ocean. And that's a really nice looking depiction of it. And then you can see a clear westerly flow. This is a latitude line straight across the whole eastern 2/3 of the Pacific. There's Hawaii. And then a little bit of cyclonic rotation into the coast of British Columbia. So we'll see, does that mimic what we see in the observations in just a minute. Okay. First, let's say something about Delta. This is maybe an hour old. So at the time, Delta was a Category 3 storm with a maximum sustained winds of 115, central pressure around 960, and moving north at about 13 miles per hour. And it's going to make landfall right there in southwest Louisiana. So let's take a look at some of the characteristics of this storm. I can never see anything, sorry. Here's the wind history. So you get a sense of where it's been in orange, tropical storm force winds, in hurricane force winds in red. A very narrow strip of hurricane force winds, but a consistently narrow strip. Brushed over the northeast tip of the Yucatan Peninsula, got back out over the open water, and here it is. These hurricane force winds will make their all the way through about the middle part of Louisiana by the time it finally weakens enough to be just a tropical storm. It appears that will be the case. Let's see something else. There's a time of arrival here. I gotta see if I can see it better this way. Wind speed probabilities is always interesting too. So here's the probability of tropical storm force winds. I wish they did the hurricane force ones. I couldn't find that so obviously. But the whole state of Louisiana has about a guarantee to see tropical storm force winds. And then they'll extend with reasonable probability, I'd say, to 40 to 50% in the yellow, even into Mississippi and southeastern Arkansas over the next day and a half. And if I had a Sharpie, maybe I'd include Wyoming. And let's see, one other thing I'll show. Two other things. So here's the 10 a.m. Friday position, and that's Eastern time of the hurricane. It makes landfall sometime between 10 a.m. and 7 a.m. Saturday, so this is probably more like 6 to 7 p.m. tonight. And it's a hurricane, but then it's a tropical storm by the time it's about to leave Louisiana, then just a depression as it moves across Mississippi and Tennessee. So rapid weakening, and currently Category 3, maybe Category 1, as it makes landfall, is a good guess. And I had one more thing I wanted to show you from this, and that was the precipitation potential. So this is really rather dramatic. Already, as we saw in the radar, these regions here, Tennessee, parts of the Western Carolinas, Mississippi, are already seeing the so-called pre-rain event out ahead of the hurricane. Here's going to be where Delta actually makes a transect across Louisiana. And that's where you get 6 to 10 inches of rain, in a couple of spots, 10 to 15. So it won't be uncommon, or won't be impossible to imagine some places get something close to 20 inches of rain. But a foot of rain in several locations in Louisiana in the next 24 hours seems to be quite a distinct possibility. So that's a half an inch per hour for a whole day. When we have a half an inch rainfall in a day, it's a substantial rain event here. People talk about it. It's just hard to imagine that that could be sustained to lead to such totals. But it's not the first time this year, as we've said a number of times. So the hurricane is a major threat for the state of Louisiana. I want to show you some upper level charts next. Start at 500 millibars. And this is from this morning. And so you can see for the major storm that's over the Labrador Sea, there's a really nicely cut off cyclonic circulation encompassing the whole region from northeastern New England all the way to the southwestern tip of Greenland. So that's a broad cyclonic disturbance in there. And the winds are pretty strong. It's 55 knots at Chatham, Massachusetts, 95 at Churchill, Manitoba, not Churchill, Halifax, and then winds in the 50s and kind of a strong jet right off the New England coast. The isotherms are every 5 degrees, the red dashed lines, and so we have a cold pool of about minus 30 right over Prince Edward Island, and then it's as warm as minus 15 or warmer to the south. So that's a pretty intense horizontal temperature contrast. Turns out it's nothing like what we saw just a couple of days ago, and that's why I wanted to bring in the Vis 5D. Off on the west coast, you'll notice a fairly intense horizontal temperature contrast associated with what looked like, we haven't seen it yet, what looked like a really strong upper tropospheric jet flow off the west coast. We'll see in just a minute that's true. We don't have any observations of winds on such a map as this, but the 300 millibar wind isotachs are plotted on the next one. This is 15 degrees of contrast, and notice that that has a really extended synoptic scale length from just off the coast of British Columbia, Washington, well towards the Aleutian chain itself. It's cut off by the time we get there. We can't see that far west. So that's a major feature. I'll come back to this in just a minute. I want to go below to 850 first. As much as I don't want to admit it or talk about it, we do have a substantial chance of seeing 80 degrees today for the first time since September 2nd, and that would abolish the chance we have of tying the all-time record of earliest last 80 degree Fahrenheit. The reason we have a chance is because if you kind of look through what looks like clutter on this map, I'll show you a colored version with isotherms colored in a little bit later, but I think you can still see it on this one. Here's a warm bubble centered right here in central Nebraska, but sort of in this whole region across the Central Plains, that's precisely coincident with a geopotential height trough. That's the classic signature of a lee-side trough. So what's been happening with this strong westerly flow across at least the northern half of the United States and southern part of western Canada is there's flow across the high terrain and then it subsides in the lee. And the subsidence forces the air to sink and it gets compressed to at higher pressures and it warms up adiabatically. And the warming up makes the column lighter, and so there's a hydrostatic response in terms of lowering the pressure or the geopotential height. So they're coincident with one another. For us, where we're positioned relative to the Rocky Mountains, every time one of these really strong lee-side troughs sets up, we find ourselves in southwesterly flow characterized by pretty strong warm advection, the strength of it depending on how much subsidence is occurring. So if the warm bubble is as warm as 26 degrees, as it is in central and western Nebraska, we stand to really have some substantial warm advection in that southwesterly flow on the eastern side of the lee-side trough. It's only 13 at Green Bay at 850, but it's 23 at Omaha, 26 at North Platte. It's a lot of warm advection. And so the temperature will rise, mostly due to the warm advection. It never hurts to have a clear sky. My only hope of staying at 79 as a high is the infiltration of these high clouds. I want a little bit of diminution of the insolation. No one's going to care if it's only 79 except me. It's going to be a beautiful afternoon, but I'd like 79 for the high. I think I won't get my wish. One of the things that works in favor of me getting, or not in favor of me getting my wish, is it's really hard to produce clouds in this region, widespread clouds. Not for lack of vertical motions, as it turns out. There's plenty of reason to expect that, especially in southern Ontario, maybe bleeding southward into the central part of our own state, in this region of fairly intense but somewhat differential warm advection. It's not the same value everywhere. And the consequence of that is, from the QG perspective, one should expect upward vertical motions. That's all well and good, but you better have water vapor in your air that's rising in substantial quantities if you want clouds to form. And the other consequence of the subsidence in the lee is that the air is really dry. And so you can make it rise, but if there's not substantial water vapor in it, you're not going to get any condensation, you're not going to get any clouds. So I think that's working against my wish to keep us below 80 degrees. If this were a little bit more saturated or closer to saturation, I feel like I got a chance that there'll be too many high clouds. That'll cut the legs off at about 2 or 3 in the afternoon and stop us at 78 or 79. I hope that's still true, but the setup, when I'm being honest with myself, doesn't make me really have great confidence in that. I think our run at the Wreck-It will end today. And I know you all feel sad for me as I contemplate that, especially Chelsea does, but it's okay. I know we'll survive if that happens. But what I wanted to do next was go to 300 millibars, just to emphasize this flow. So this is 12Z this morning at 300 millibars. Some of the jet intensity has dissipated as the week's gone by, but it's not insignificant to see 40 and 50 knot winds coming across the high terrain, and there's a lee side subsidence, not at this level anymore, but further down. Here's the strong jet off the Pacific. Remember, we had a strong 500 millibar temperature contrast that exactly mimicked the position of this ice attack maxima. And 183 knots is a really strong jet maxima. Okay, so that's one for the books. And that's going to be a major feature for the forecast, especially in the medium and long range. Immediately downstream of the jet exit region is already a little bit of trophiness. We saw that in the satellite picture, right, when we saw the clouds kind of taking that cyclonic shape to them and then coming on shore along the coast of British Columbia. This is going to further evolve for reasons that are in some ways fairly straightforward. At a really strong, the exit region of a really strong jet like this is a big speed variation. And so there's imbalance on both sides of this. Well, there's imbalance when you try to decelerate, and the air is forced to rise on the exit region on the left side and sink here. And if it's rising here where it's already cold, then the thicknesses get smaller, and the geopotential heights, presumably at all upper levels, get lower. So whenever a jet is on the western side of a developing trophiness, I always expect the trough to get a little more intense, because it will cool, those columns will cool. And we'll see that in the forecast. I won't say more about it now. But I just want to do one last thing while we're here, and maybe it's redundant and doesn't need to be done. But this is a movie of the 500 millibar flow over the past week, and I'm stopping it just a little bit ahead of where I want to see it go. So here's a strong baroclinic zone off the Pacific coast. There's kind of a broad southeastward directed flow over the Central Plains and western part of Canada. So I want to show you what happens at this level over a couple of time periods. So there's 06 on the 6th. I guess I'll stop right here. 12Z on the 6th. Oh, sorry, 0Z on the 7th. And at which time there's a very straight flow running all the way from northern Indiana back to central or northern British Columbia. That's characterized by a pretty nice baroclinic zone, but it's not really very tight. You know, it's a plus 10 or minus 10, I mean, on the warm side, and maybe minus 22 on the very coldest part of it, right over Lake Winnipeg. So, but it's a broad region of a pretty decent 500 millibar temperature contrast. Watch what happens in a very short time. I'll just go ahead to the 12Z. The very next set of observations indicate a really rapid intensification of the baroclinic zone at this point, just over northern Michigan, where it's as cold as minus 25 over the Upper Peninsula, and it's as warm as, minus 10 over Chicago, or far south, almost Detroit. So we got a really sharp horizontal temperature contrast at 500 millibars that develops. As that develops, the trophiness seems to get more intense at 500 millibars. At the same time, one more time ahead, look at how much more sharply curved the flow is by the time this feature moves off to about the New England coast. And 5, 10, 15, it's minus 22 at Albany, and it's minus 10 at near New York City. It's even warmer than that to the south, like if you had an Atlantic City ob, somehow it's not reported here, it's probably warmer than minus 10. So we've gotten a distance between the minus 22 and minus 10 isotherms at 500 has shrunk by probably a factor of 3 in one day. So this is a really intense, and look at how long that region of fairly intense gradient extends. So a very rapid development of an upper level front that is usually coincident with a rapid increase in the 500 millibar vorticity. And even without plotting it, you can see in the winds, you're going to have 110 knots at Chatham, Massachusetts at 500 millibars. That's a strong 500 millibar wind. Only 30 at Portland. So there's extraordinary horizontal shear there, and that's in a place where the flow is curved too. So you both have shear and curvature vorticity that develops quite rapidly in this location over a very short amount of time. And the consequence near the surface, I'll say, not at the surface, let's go to 850 and pick up those same couple of times. Let's see, that's 12Z6. That's 0Z on the 7th at 850 millibars. It's hard to really pick out any single region of low geopotential height. Maybe just north of Lake Superior you see a little bit of trophiness coincident with a slight bit of a thermal ridge there. Watch what happens at the next time. This is while the upper front is really getting revved up. There's your little depression over Ontario. And at the next time, it's a much more intense cyclone. And it's right over, northern part of Maine. Remember we had our 500 millibar vorticity maximum was right about here. And so this is a nice response to the presence and development of the development at upper levels. Okay. So let's see, what did I have next? Oh yeah, I was going to show you this, but I think I'll skip it. Well, I did want to show you this. This is a 6-hour forecast from the GFS, valid about right now at 850. More reason to suspect 80 degrees is definitely a possibility today. It's very warm at 850 to our south and west, and the winds are strongly from the south and west. The warm advection will not let up this afternoon. It's not going to suddenly stop. It's going to even increase. And so it might fight a little bit of retardation by some high clouds, but as I mentioned, I think the high clouds are less of a threat than they would be under conditions that didn't have a lead trough upstream. Look at how intense the baroclinic zone is across the northern side of the lakes, and that leads to the production of differential warm advection. We're probably going to see some vertical motion forecasted in this region. Not so much here, and even if we did, the air is too dry to really turn that vertical motion into clouds, and that's what I have as a concern. Here's 500 millibars at the same time, just to point out that there's not much forcing at upper levels from the traditional perspectives to expect vertical motion over the state. It's pretty zonal flow. These are a little weak vorticity maxima. You can hardly believe they even exist, perhaps. And so there's not any organized regions of positive vorticity advection in the middle troposphere that are not mimicked underneath. So I don't see any strong forcing at 500. Here's the 700 millibar vertical motions, and they tend to be concentrated over the northern tier of the lakes, perhaps in response to that differential warm advection over that same region at 850. So I could show you more, but I don't have time. The vertical distribution of the forcing that could produce the vertical motion is very much confined to the lower part of the troposphere in this setting. And so there's just no particular reason to expect clouds to develop today. And here's part of the reason. In the pink shading is the relative humidity. I think that's in values that are below 50%. So the air has just not got enough water vapor in it, even if it were rising. And finally, all the forecasted precipitation valid at this time is up there north of the lakes, where the differential temperature advection producing updrafts, the air is so dry it's got to keep on being lifted at probably up to 400 or 500 millibars before it can finally condense and then have a threat of precipitation. So we don't have that. But even in the thickness field, we have continued warm advection. It's not looking good. Okay, I want to show you some things about the Labrador Sea cyclone before we go to a forecast. Oh, that's not what I want to do. Okay. So in order to do that, what I did was I took the, oh, something seems a little bit crazy here. Okay, we're back. What I did is I took the 0Z on the 7th of October GFS run, and I went back a couple of days because the event of interest is right now in about this location. I wanted to see where it came from. So here's the broad scale 500 millibar potential temperature map from that time. Okay, I'll make this a little bigger, I guess. Watch this, Pete. Oh. Watch this, Pete.
Well done, John.
Yeah, thanks. Come on. Jeepers. I thought I knew what I was doing.
Middle button.
Yeah, middle button, there's no buttons, that's the problem. Okay, it's
There you
optional. See, I had them all memorized, Greg, and I forgot what they were, so. Okay, so that's as big as I can get it. A little bigger. A lot of counties in the eastern half of the United States. Look at this broad but not particularly intense baroclinic zone at 500 millibars. These are theta every couple of degrees. I think it's every 3. And then these maps are going to be shown from the forecast every 3 hours. So this is 0Z on the 7th. This is, oh, I got to get a step. That's 3Z, so you can see. And then watch what happens. 3, 6, 9, 12. What's happening in that baroclinic zone? It just gets sharp in no time. You see that? It's involving the same bundle of isotopes, but look at how much sharper that is. And not just over Wisconsin, all the way along its length, really. But it gets really intense, fast. Okay? And intense meaning that isotherms just get closer together. And let's keep going. Look at this. What is this? So that's a really intense upper baroclinic zone. Seemingly comes out of nowhere. And without showing you all the details, because we'll save that perhaps for another time, in the wintertime, this happens because you're forcing, most likely, because you're forcing the air to sink on the warm side and maybe forcing it to rise or not do anything on the cold side. And that produces an intensification of the temperature contrast at 500 millibars. And I think this might be the time where I have a nice cross-section to show you. Yeah, well, let's see. Is this the best one? Yeah, I think it's close to the best one. Let's go right there. So let's take a cross-section through it right there at this particular time. And so that's over, that's 3, 6, 9, 12 degrees horizontal temperature contrast from Washington Island to Appleton. So that's a pretty small distance for a 500 millibar temperature contrast. So let's see what it looks like in the vertical. So there's the, oh man, someday we'll be able to do this right. Here's the vertical cross-section depiction of that. And that is a pretty intense upper level front. The green lines are potential temperature isotopes every 3 degrees. This thing extends all the way from the polar tropopause down to somewhere around 750 or so millibars. And there's even a hint of some hard low-level baroclinicity that might have something to do with the upper front, but it's not really well connected. Now let's see what the potential vorticity looks like.
Hey, John. Greg was going to say something.
Yeah, sorry.
Yeah, well, you could probably show the potential vorticity better, but the isotherms are very expanded up there just to the south of that baroclinic zone. And
right in here.
Yeah, I'm suspecting that's outflow coming off of Delta.
Remember where we are. Let's see, is that possible? Where?
Well, you showed
yeah, I
picture
guess that's
where
right.
there
Yeah,
was
that's
you
right.
could see the plume literally in that other.
In the radar, that's right. Yeah, so that's in the
not
right
even
spot.
in the radar. You had another picture. I forget what it was, but you could see a plume connecting right to Delta on that.
Yeah, so Professor Tripley's pointing out the vertical separation of the theta isotopes here is unusually large in this location, and that's almost surely going to be characterized also by very low potential vorticity, and low potential vorticity resides in the troposphere in the tropics. And so sometimes these things are actually manifestations of outflow from such tropical disturbances. Were we in a classroom with unlimited time, we would do this on the fly. We'd say, okay, let's initialize some trajectories right in here and see where the air came from. I bet you're right.
And what that produces is what we call an overfold, where the tropopause folds over from the south, over the top, and that creates, by default, this folding down that we usually see from the northerly flow. You have both here now. You have the northerly quasi-geostrophic flow pushing the tropopause down. This is folding it over the top, and I think the two together are creating a great enhancement. We've done a number of studies of tropical cyclone outflow like this, and in each case, it produces a baroclinic zone at the surface. So I'm guessing that's exactly what this is.
And another characteristic of what you're talking about is sometimes you can see an upper level front. You don't see a lower stratospheric front. So these isotopes are pointing upward to higher elevation you cut across them horizontally, that's a strong temperature gradient in the lower stratosphere. These are being pushed upward. In many instances, they're pushed upward by the inflation of this layer, and that's outflow. So it comes in and it squeezes them up.
As you get closer to the jet, the
What you'd be right about
anticyclonic
here.
vorticity dominates the potential vorticity. So I think if you look at the potential vorticity, you'll see it pushed much more toward the baroclinic zone. It should be almost continuous. In other words, you got very low potential vorticity where the
Right here.
right there.
Yep.
But if you go to the other side, yeah, that's still very low over there because of the anticyclonic shear.
Yeah, and not till you get back on the cyclonic shear side of the jet.
And so what you have is this push of low potential vorticity up against the polar tropopause.
Yeah, and I've got the PV ready. Here it is.
Yeah, there it is. See,
And you
there's
can
the wall.
see, I hope you can see there, all the lines are double thickness, but in purple is the PV. So you can see, here's the bulge of this low PV that squashes this gradient, and this is where the jet's gonna be. I don't have the jet, but I'll get it in just a second. And so that's part of this structure. The other part is probably been, and we don't have time to show it, but you could show it again by initializing trajectories. Just say, where did this air come from? And undoubtedly, we're gonna find that that air has sunk from higher elevation over a long period of time along this front, and that drags the vorticity, which is, or the potential vorticity in the stratosphere, which is mostly stratification, drags it into the middle troposphere, and suddenly it manifests itself as a vortex structure, and that's what accounts for the intensification of the 500 millibar vorticity, which I'll also show you in a minute. And then downstream of that's where you get your cyclogenesis. So it's all kind of put together, how these things work in sync, in concert. So let me get the speed on here quickly, just to see what to illustrate Professor Tripoli's point about the speed. Okay. And I think I'll take the PV off, just because there's going to be so many things on there, and then we'll take a look at this. So there's the isotypes. Oh, I didn't put them the way I like to, let's see. Let's do them every 10, starting at 30 knots, or 30 meters per second. Okay, so I think we did that. Okay, so there's the isotachs on top of the isotropes. And so here's a nice relationship where there's strong horizontal temperature contrast. In the green lines, there's strong vertical shear of the winds themselves. Where there isn't much horizontal temperature contrast, there's almost no vertical shear. You can see the purple lines are straight up and down, and they're evenly spaced because they can't exceed a certain value of the vorticity. Once you get past the jet core, there's no limit to what they can be. So they always look asymmetric like this, with the most intense band of isotrope gradient, both the vertical and horizontal gradient, right along the upper front. So that's pretty nice. And the maximum wind is 70 meters per second in the middle of that thing. Okay, so the last thing I'll show you with the Viz 5D is, let's go back to the top, get rid of all this, and all I'll do, unfortunately, because of time constraints, is show you the PV. Let's go back to the beginning. And mean sea level pressure. And these are only mean sea level, mean sea level pressure isobars below 1,000 millibars. I'll put them in a different color. That doesn't work.
You need to put them up high above the surface.
Well, they are, but the color is bad. So white, I think, works okay. So those are the mean sea level isobars at the top. So you can see them on top of the PV. Maybe I'll put the map there too so you can see where we are. Okay, so there's the map. I think you can see everything. Okay, so remember we had that broad baroclinic zone at the initial time at 500 millibars. That corresponds to this trench in the tropopause. Here's the cyclone that's over northern Hudson Bay. It's not the one we're talking about. So let's go forward and see what happens as this trench gets more intense, and that's characteristic with the intensification of the horizontal temperature contrast and the vorticity, which I didn't show you. I didn't have time to show you that.
You sure you don't want to lift the height of the MSLP surface all the way to the top? just so nothing, you don't have anything.
I thought it was. Is it not at the top?
No, it's at 14.5.
Oh, yeah. Okay, there we go. Okay, I don't know if it would have mattered, but that's a good point. So let me also make this bigger.
I don't understand why you don't see the hurricane now.
Well, because I only put 1,000 millibars and lower.
Yeah,
So I don't know why the hurricane's not there. Maybe I did put that in there. Let's see. Yeah, I'm up to 18 kilometers, so I don't want that. Yeah, so I don't know why. Anyway, I guess it just proves that these things are weak little disturbances, those tropical cyclones. Okay, let's go forward. And there, right there, you can see the first 1,000 millibar isobar sprout out of the front end of this developing upper front, and the front end of it is where the vortex is maximized. And watch what happens there. And that's where we get the development. And look at how it stays tied to that intensifying upper level vortex structure that's kind of in the red. And there it goes off to Greenland into the Labrador Sea. So that's what we saw in the satellite picture at the beginning of the discussion today, approximately the same time. This is a really intense cyclone. This is 62840 72 970 millibars in the middle of that thing. And there's Delta 996. That's just because it's probably wrong initialization or something. But nonetheless, there are the storms. And look at how intense that thing gets up there in the Labrador Sea. And you maintain this really deep tropopause trench in the red. So this kind of development is going to begin to happen every week across North America and adjacent waters. And so it's kind of fun to point them out. Maybe one day we'll just do a whole discussion of just one of these things for the whole hour and not make it part of a larger discussion because they're so interesting. But are there any comments or questions before I move to the forecast? And it'll be quick, the forecast. Okay. So let me go there. And what we're going to do is, I haven't figured out what's the best way to do this. But this is going to be my guess. Just want to look at a series of 3 panels at each of several times. This is the 18-hour forecast from the 6Z run, or 12-hour forecast from the 6Z run of the GFS. So this will be valid right about now. This is 300 millibars. And quickly, here's the strong jet that we saw in a number of depictions in the current observations part of the discussion. And here's the trophiness right off the coast of British Columbia and northwestern Washington. And then we're going to go to 850, and we're going to go to the surface at sequences of these things. I think I do them every 12 hours for a period of time. So there's the trophiness off the coast at 850 millibars. There's not really an obvious cyclone yet, maybe just a little bit of a closed geopotential height contour off the north coast of British Columbia, but there's a broad cyclonic flow. And then it's really warm over the high terrain. There's Delta making landfall, about to. And there's our little cyclone to our north that we saw with the clouds and, the forecast precipitation. And then at sea level, there's a weak cyclone in southern Canada. And there's not much of a cyclone off the west coast, maybe 986, but that's tied more to this broader trophiness over Alaska. And there's a precipitation maximum along the southern coast of British Columbia, largely orographic in nature, I would suspect. And then if we go to the next time, it doesn't work the way I hope. This is valid now tonight at midnight. The jet is still off the coast. The trophiness maybe looks a little different, but I'm not going to really make a strong argument for that. But the basic structure is coming on shore of a really intense jet preceded by an upper trough. And then at 850, one doesn't see a big difference, except that it seems as though there's beginning to be a cyclonic circulation that's dragging some of this warm air from the Intermountain West poleward into southern Saskatchewan. And this is midnight, don't forget, maybe 10 o'clock local time out over here. So this is not daytime heating. This is just circulation dragging warmer air poleward. And at sea level, still one doesn't see an individual cyclone yet on the west coast. It's maybe a little bit of a lee trough in the lee of the Canadian Rockies. At the next time, I think the troughiness is discernibly more intense at this time. This is now valid tomorrow afternoon at noontime. That's a sharper trough, and it's now just inland across the Coast Range of Washington and Oregon, 168 knot jet still. So I'm expecting we'll see a little bit more development there, especially since there's a nice downstream ridge, really sharper upstream trough. Right in here is where the upper divergence will be maximized over the British Columbia, Saskatchewan, or Alberta border. So let's see what it looks like at 850. Oh yeah, there is a little bit of a central circulation, and right about that spot. See that? So that's a synoptic scale cyclone developing over rugged terrain, but notice how the dragging of the warm air is continuing into western Canada. Part of that warmth is lee side, no doubt, but part of it is responding to the circulation that's imposed by that development. And there's the cyclone, finally. It's kind of got its own little structure on the border of British Columbia and Alberta. 988 millibars. See, the thickness field has a nice ridge right in there. That's where the warm air is. And let's watch what happens as we keep going forward. Okay. So this one now is valid at what? Midnight Saturday. Same basic structure, it's just moved eastward, and so I think the development will be a little bit more in this location, maybe central Saskatchewan, heading into Alberta into Saskatchewan. And there's the 850 flow. Pretty intense disturbance right in this location, right on the border of those two provinces. And look at the warm tongue that's going straight up into central Canada. And then there's the cyclone that's fairly intense too. I think we had 996 before, now we're down to 984. So that's a pretty intense disturbance, and the thickness gradient looks the same as it did prior to that. Strong warm advection into the central plains of Canada. The polar bears are coming down toward Churchill, Manitoba, which is on the west coast of Hudson Bay. They're not going to like this. It's a little too warm for them, I'm sure. And they can't do much about it. Now I think we go to midnight on Sunday. Midday on Sunday. Structure looks the same, but I think the ridge and trough are closer together. That makes the upper divergence more intense north of North Dakota. And so I think that's probably the likely spot of the cyclone, and it does look like that's the case. And continued flood of warm advection into central Canada. The cyclone's more intense. And I think at some point I stop going every 12 hours because that gets to be a little much. Oh, what am I doing here? Oh, yeah. Okay. Same structure, I think. Jet now beginning to undercut the upper low that's developed over this period of time. This is now valid Sunday night, midnight. Upper divergence max probably right about there, and that's kind of moved a little eastward to the border of North Dakota and Minnesota, but just north of the border. There's 850 millibars. Very intense disturbance has developed over central Canada, and there's a flood of warm air all the way to the southern shore of Hudson Bay. This is unusually warm for them, and that's what the cyclone looks like. So we're developing a really intense low-level disturbance, which is dragging warm air off the central part of the United States part of continental North America, and really driving some warm air into Canada. Let's see, in the interest of time, I'll go to another time. Just want to show you what happens. Eventually, this is now midnight Monday. This circulation has become quite intense. And notice what it's doing. It's starting to drag polar air that's north of the North Slope in Alaska and over the archipelago. It's finally starting to drag that into its circulation. And then it's going to, as time goes by, intensify the cold advection into the central part and southern part of Canada. Puts us at risk for a fairly chilly period a week from today. We're not going to be anywhere near as warm a week from today. So watch this. So that's 850. That's 850, I think 24 hours later. Then you can see the cold air is funneling in on the western side of this stationary upper low that's sitting on the western shore of Hudson Bay. And this is all initiated by the onshore movement of that upper trough that's currently off the west coast. Look at that, cold air is expanding. And it's not expanding because the air is rising on that side of the cyclone. That's just downright cold because of advection. And a couple more times, you can see it just keeps getting expanded even more. Just remind you of the time you might not be able to see. This is midnight on Thursday next week. This is chilly for us. We're into the, +2 or -2, I forget which one, much colder air up to the north and nothing stopping it, strong northerly, northwesterly flow. So a week from today, we stand to be sitting in some pretty chilly air, courtesy of a very intense development over central and northern Canada. By this time, this will be midnight next Friday, that is quite stationary, as the jet first helped to develop it and then undercuts it, and therefore it's kind of divorced from the westerlies and it won't move. And look at these temperatures. We're going to get well below zero at 8:50 by midnight Friday next week. So overnight lows in the 30s for sure, probably a couple of places colder than that. Greg's house will be colder than that. Maybe even the first snow flurries of the year. It's not impossible. So a big change from today, a week from today, and it's all instigated by a feature that's sitting off the coast right now that will gradually develop a fairly intense disturbance that becomes quite stationary. So I thought that was an interesting evolution. So that's all I have. Are there any comments or questions? Oh, I came in on time. I can't believe it. Okay, so next week will be the last time that I'll give it for at least a month. And then 751 students, please get your partner names to me and pick a week. And I guess if I don't hear from you all by next Friday, I'll just assign weeks to everybody and then figure it out. Okay? Okay, thank you, Pete. Thanks, Greg, for comments about the jet and the hurricane. The hurricane was in that GFS. It was just kind of weak in the sea level pressure, I guess.
I think those plots are from the 1 degree data, so it might just be sampling issues.
Yeah, it could be, okay.
Not seeing it.
Yeah.
Well, the one that you were showing when I was looking at it initially, I think was a historic block before.
Yeah, it was 0Z on the 7th, so that would have been Tuesday night.
Yeah, that's where it started. That's right. That's where it started. And in fact, that's the reason. That's where it started. Yeah. It was a couple of days
But
ago.
even when it got into today, you were only showing like 996, and
Yeah.
it was deeper than that. It was in like 9.
It's 960, 956.
Yeah.
Yeah.
I wonder what it looks like on the half degree stuff from those Python maps.
Well, I don't know.
I would imagine that shows it a little stronger. Of course, that's a different model run too, but
I got to get rid of all this. It's going to take a while. So, what the heck is this? Yeah, you know. Pete, you can probably see better than me. You want to come up and get it?
sure.
Because I just can't see. Thanks.
Yep. That's why I started wearing my bifocals instead.
They don't work for me. I tried them one summer. I was riding my bike home like Mr. Magoo. I couldn't see anything. So, okay, there's the web. All right, that's where you want to be.
So this is 12Z today.
Yeah, it's well below 1,004. So that's 40, 96, 92, 88, 84. There's probably a couple more in there. So and it looks like I don't know, maybe a 978 or something. So it's not as deep as the actual disturbance, but it's a lot better than what we just saw.
The other thing too is the Viz5D, the way I generate those from the GFS. Here's the loop of the, oops, that's not the right one. Hold on. Put up the loop of the 850 while I'm talking. Those loops are actually generated. Is that? Looks like it's jumping back. There must be something up with the 12Z. The way I generate those Viz5Ds is I take the 1 degree GFS and I interpolate it onto an 80-kilometer version of Greg's model. So there's a lot of resampling and interpolation and stuff going on there.
I don't need to save any of that stuff. So.
Here's from the 60 run. So this is the run you were showing. This should show that cold air.
Yeah, look at how that circulation just drags the cold pool that's sitting up over the archipelago. It's nice to see it in animation. It just gets dragged into this circulation, and then it empties the archipelago cold pool. That just disappears.
Yeah.
Largely.
Can I say something on this? I think this system here, this Bear Clinic system is an excellent example of an extratropical cyclone and what's actually happening physically. And I would differ in your explanation of saying the cold air is dragged in. I would say the cold air is the system. The cold air next to the warm air is overturning, and that's what's creating the energy that creates the low pressure. What's happening is the cold air is dropping underneath. It's sinking from a higher elevation to lower the center of gravity of potential energy. It's sinking down underneath, and with Coriolis it hooks to the cyclonic direction. So as it comes down and hooks, and the warm air is doing the same thing, it's going over the top. And as the cold air drops, it draws the warm air over the top, and that lowers the pressure at the surface, because as the cold air sinks, it leaves a deficit of mass at the higher levels. And that creates kind of a vacuum over the region where the warm air is. I'm not exaggerating, it's not a vacuum, but it lowers the pressure in the column. And that lowers the pressure at the surface, and that draws the warm air up around it and over the top. And in the end, what's happening is the warm air is going north over the top of the cold air, which is going south at the same time. And in the end, the center of gravity has dropped of the whole system. And so in the end, the average height of the atmosphere has dropped, and the potential energy is released. And that's what's causing all the wind and all that spin up, is the release of that energy. Which is I try to tell the class, that's just a fundamental difference in what drives those systems compared to what drives a hurricane, which is just warm air rising, and not so much cold air sinking. But you can see it between the two things here, and in that simple idealized model of an extratropical cyclone, I showed even better, where you can just see the hooking around. The cold air hooks underneath, and the warm air hooks over the top, and that's how they do it. And they do it through the hooking motion because of the rotation of the Earth. They cannot do it on a bigger scale, because you build up these temperature contrasts over a very large area. It can't just overturn because of the rotation of the Earth. But when you get a small scale and you perturb it, it can start to overturn as an eddy on a smaller scale of a couple thousand kilometers, which is what the cyclone is. So in the end, after this extratropical cyclone occurs, the mean position of the cold air has advanced south. That's the net effect of the whole thing. To advance the cold air to the south, stretch, and then it's going to become more shallow, because it was up here and it went to the south, that lowered the center of gravity, that released the energy, but it also advanced the cold air. It can't just advance on a big scale because it's balanced against the rotation of the Earth. But because the effects of rotation get less at finer scales, it's able to do it at this scale. And that's basically what the ultimate physical reason is for these extratropical cyclones. And this is just a beautiful example of that, the way you see the cold air just going underneath and the warm air shooting over the top. And when it's all done, it's occluded, right? And that's the end.
That's the whole end game, because the occluded state is a state where you have the lowest potential energy. There's no doubt about
That's
that.
right.
Yeah. Yeah, so it is a very nice development, and it has elements of some more graphic influence, but it's mostly a basic, substantial mid-latitude development, so it's really neat. Okay, I guess we're done for the week. So we'll see you all next Friday when it's 52 degrees and cloudy, and you'll be wishing for 80 degrees, as much as I'm wishing against it today.
All right. Thanks, John.
Thank you, Pete. Thanks, Greg.
Hey, Greg.
I stole this from room 811 because I